Hello, everybody, and welcome to another wonderful day of chemistry. So far, this chapter, we've covered a whole bunch of different entropies. We've covered the entropies for heating, for cooling, expansion and compression, and phase changes. So there's only one real entropy we have left. Time for entropies of reaction. So what we're really going to be focusing on here is the entropy of the system actually undergoing reaction. And just like with changes of state, every reaction is going to have a characteristic entropy associated with that change with the change. So we can usually find most of our entropies of reaction simply by using the fact that entropies are a state function the same way we dealt with enthalpy. So we can go ahead and sum up all of the entropies of our products and then subtract out all the entropies of the reactants, again, paying close attention to any stoichiometric coefficients here. And again, so we can literally just do this as kind of the sum entropies of products and reactants. We're noticing that for reactants, the coefficient here will be negative, subtracting them out. Now, again, just like before, we need to go ahead and pay close attention with what our reference entropy is going to be. Now, in this case, we actually have a bit more of a choice than we did with enthalpies. There's going to be two major options. We're often going to have our reference entropies as actual third law entropies, because it turns out you can actually figure out the absolute entropy for any number of substances. However, it's also common to have them listed as entropies of formation. So in the same way as enthalpies, this will go ahead and refer to forming the material from elements in their most stable state. So let's go ahead and kind of compare and contrast this when we're looking at determining the entropy for a formation reaction. In this case, this is actually a reaction you can do. You can take coal dust and you can add in hydrogen gas to make methane. Now for here, we're going to assume the solid carbon is our most stable state, so that would be graphite, adding in hydrogen gas to make methane. Now, if we do this, we can calculate this again, products minus reactants, but we have two different entropies we can choose from. We can go ahead and choose from the third law. Notice here, no major subscript, or the entropies of formation. Now, from the third law, we'll simply go ahead and take the entropy of methane minus the entropy of graphite minus twice the entropy of hydrogen, because again, I have to account for that too. So then we'll go ahead and take all of these together, noticing that the units here are going to be joules per mole Kelvin. So this is actually a molar entropy of reaction. And while not explicitly stated, most entropies of reaction will be given as molar entropies, not size extensive entropies. So it turns out that entropically this reaction is unfavored, which makes sense because we go from three different reactants, two in the gas phase, to a much simpler single methane molecule. So this is entropically unfavorable. Now, if I'm using the formation, well, in this case, we get lucky because our two of our compounds in their elemental state. So I can go ahead and just take the difference and again, get the same value. So noticing it's equally equivalent to use third law entropies or entropies of formation. Now, one of the reasons I really want to bring this up is when you go ahead and hunt down entropies to figure out an entropy of reaction, you have to pay very close attention to which one you're using. Because you can use either, but please never mix and match. If you do, you will get a very wrong answer. So keep an eye out for that. And again, pay very close attention to which one your reference table will be listing. Now, one of the other things we run into is the same exact problem we ran into enthalpies, which is that all of our entropies of reaction can be go ahead and determined at any temperature. And so the entropy at a high temperature may not be the same as the entropy of reaction at the classic room temperature 25 degrees C that I'll go ahead and find in a table. So we can go ahead and correct for this using a very similar process to what we did for Kirchhoff's law, where we go ahead and just use thermodynamic cycles. So if I want to go ahead and go from a reactant at an elevated temp to a product at an elevated temp, I can either go ahead and take the difference, but if these values aren't obtainable, I can instead take the long way around. Look at the temperature change, then take the entropy of reaction at that temperature. Often this is going to be your standard state entropy, and then again change the temperature again. So again, if I'm looking at the entropy of reaction at that T2, I can go ahead and use the fact that first I'm going to go ahead and in this case, cool the system. So here we've got a negative CP because I'm going from T2 to T1, and that will just flip the direction. So that's where the negative sign comes from. If I'm going from T1 to T2, we have the straight option. Notice here on the left, this is going to be the heat capacity for my reactants, and on the right, the heat capacity for the products. Now I can go ahead and put all of these together. Again, noticing here I've got my entropy of reaction T1, so I'll pull that out front. And then notice I have the same temperature difference in both cases. So that means I can combine the heat capacity. So it'll be the heat capacity of the product minus the heat capacity of the reactant, which is our good old friend, the change in heat capacities for a reaction. So notice this looks very similar to the Kirchhoff's law. Only difference is we're dealing with entropies instead of enthalpies, and that instead of the delta T here, we have the natural log of the temperature difference. So again, slightly different formalism built on the same principles and gets us a lot of the same information. So that kind of wraps up how we can determine entropies for a system. But remember, the original reason we started this chapter was trying to look at how favorable or spontaneous a reaction is, which means we're going to go ahead and take a step back, and instead of focusing on entropies of a system, we're going to look at entropies of the universe, which is annoying, so we're going to go ahead and come up with a different state function to make it a little easier. So next time, the Helmholtz free energy. Until then, take care.